In this video, I'm going to explain in detail about relations. I had already made a video regarding relations of 11th class mathematics, and I had shared the link in the description box. If you have not watched that video, please do watch the video first because it contains basics of relations. So now in this video, I'll concentrate on relations which are from a set to itself. So a relation from A to A is nothing but its subset of A cross A. A cross is nothing but Cartesian product. So Cartesian product of two sets, that is also already defined in the relations of 11th class mathematics. So if you have not watched that, please do watch first to get to know about the idea of Cartesian product. So a relation from A to A, here we are concentrating on the relations from a set to itself. It is subset of A cross A. The example is, take A with the three elements 10, 20, 30. Then another set is also same A, 10, 20, 30. I have defined a relation less than on from A to A. So 10 is less than 20. So 10 is less than 30. They are connected. 20 is less than 30. Then no other element is connected. Therefore, this relation R contains the elements 10, 20, 10, 30, 20, 30. So this is how we define a relation on a given set. It is called as a relation from A to A. So when you have such relations which are defined from a set to itself, then we can define some types of relations. A relation R which is defined on a set A is said to be, there are different types like reflexive, symmetric and transitive. Even before that, you can have a null relation, and one more is universal relation. One more is universal relation. Okay. Null relation means if there is a relation under which no element is related. So in such cases, we call that relation as null relation. So the Cartesian product subset, empty set is subset of every Cartesian, every set. Therefore, null relation represents the empty set. If R equal to null set, then such relation is called as null relation. Universal relation is if R equal to the entire Cartesian product of that particular set, then we call it as universal relation, where every element is related to every other element of the set, another set. So we call such relation as universal relation. So out of different types of relations, these are mandatory relations. Then there are different types also, like reflexive, symmetric and transitive. Let us look into that. What is meant by a reflexive relation, symmetric relation and transitive relation? So reflexive relation is nothing but if A comma A belongs to R, if you have ordered pair of the form A comma A, if that is there in the relation for all possible values of A in the set A, then we call it as reflexive. Reflexive means it is a reflection of itself. That means A is related to itself. A comma A belongs to R, in the sense A is related to A. In case for every element of that set A is related to A, then we call that relation as reflexive. The relation is symmetric if whenever A is related to B, then B should also be related to A. Then such relation is called symmetry. Symmetry in the sense mirror images of each other, like that. Symmetric. Transitive in the sense, in case if A, B and B, C are related, A is related to B and B is related to C, then A should also be related to C. A comma C belongs to R. That is what transitivity says. So symmetric and transitive relations, they have to be checked if you have ordered pairs of the form A comma B, or here A comma B and B comma C. If you don't have ordered pairs of the form A comma B and B comma C, then no need to check, it is transitive itself. See, for example, let us take one set A equal to 1, 2, 3. Then I have defined different relations on the set A. I have to check, is it symmetric, is it reflexive, is it transitive? That we will do it now. So now the first relation, you two, for all elements of A, you have ordered pairs of the form A comma A. So 1 for 1, 1 comma 1, 2, 2 comma 2, 3 comma 3. Therefore, this relation is reflexive. Now, is it symmetric? That we have to check. Symmetric in the sense, if you have A comma B, B comma A. Usually when A and B are distinct, then only you have to check for B comma A. Here they are all unique. Here they are all same. Therefore, 1 comma 1, its reverse ordered pair will be only 1 comma 1 that would be there in R1. So this becomes symmetric. Transitivity means when you have ordered pairs of the form A comma B and B comma C, then only you have to check for A comma C. If that doesn't exist, then it is not transitive. But if you don't have such ordered pairs, then it becomes transitive only, because there is nothing to disprove here. If you want to say that it is not transitive, then you have to show ordered pairs of the form A, B and B, C such that A, C is not there. You can't establish that because you don't have ordered pairs of the form A comma B, B comma C, therefore automatically becomes transitive. So it is reflexive, symmetric and transitive. Now R2 you consider 1 comma 1, 2 comma 2, 3 comma 3, 1 comma 3. So in this case it is reflexive because for all elements of A, you have ordered pairs of the form A comma A, 2 comma 2 is there, 3 comma 3 is there. Other than this you have an extra ordered pair, no, not a problem. The requirement for reflexivity is that for all elements of A you should have ordered pairs of the form A comma A. That is satisfied. Now you have to check, is it symmetric? So this is not symmetric. Very clear it is, because 1 comma 3 belongs to R2, but 3 comma 1 does not belong to R2, hence it is not symmetric. Then you have to check for transitivity. The transitivity means 1 comma 1, then 1 comma 3, 1 comma 3. It is already there. Then 2 comma 2, there is no ordered pair starting with 2 comma 2. You can leave it. 3 comma 3, there is no ordered pair starting with 3 comma 3. You can leave. Then 1 comma 3 and 3 comma 3. 1 comma 3, that gives you again 1 comma 3, which is there in the given relation R2. There it becomes transitive. So this is reflexive and transitive, but not symmetric. Now if you consider the relation R3, 1 2 comma 2 1, so this relation is not reflexive. That is because for all elements of A you should have ordered pairs of the form A comma A. For 1 there is no 1 comma 1, for 2 there is no 2 comma 2, for the 3 there is no 3 comma 3. But if you show 1, that is enough. It is not transitive also, not transitive. That is because look here, 1 comma 2 and 2 comma 1 belongs to R. So 1 comma 1 should belong to R3, but 1 comma 1 is not there in R3, therefore it is not transitive, but it is symmetric. This relation is only symmetric. That is because 1 comma 2, 2 comma 1, the reverse ordered pair is there in R3. Now take R4, this relation 1 2 2 1, 1 comma 1. This is clearly not reflexive. Reflexive in the sense 1 comma 1 should be there, 2 comma 2 should be there, 3 comma 3 should be there. None of them are there in R4. Therefore only 1 comma 1 is there, but 2 comma 2, 3 comma 3 are not there. Therefore it is not reflexive. Is it symmetric? That we have to check. Yes, 1 2 2 1 and 1 1, its reverse ordered pair will be 1 comma 1. It is not reflexive, but it is symmetric. And you have to check for transitivity. It is not transitive. You have to be very careful in problems like this, because 1 2 2 1, 1 comma 1 is there. You can't conclude that it is transitive. You have to check for all possibilities. 2 comma 1 starting with 1, 1 comma 1, yeah, 2 comma 1 is there. 2 comma 1 then starting with 1 comma 2. You can go in reverse also, not a problem. Now 2 comma 1, 1 comma 2, then 2 comma 2 as per this. So you have ordered pair 2 comma 1, then you have ordered pair 1 comma 2, then it gives you 2 comma 2, but which is not there in R4, hence it becomes not transitive. If you just check for these ordered pairs, then it looks like transitive, but it is actually not transitive. Now R5, this is not reflexive. The set remains the same. Set is A only, not reflexive. The reason remains same. 1 comma 1 does not belong to R5. Then here it is not symmetric also, because the reverse ordered pair is not there, but it is transitive. That is because you have to check it. 1 comma 2. Is there any ordered pair starting with the 2? No. If you have ordered pairs of the form A, B, B, C, then only check for AC. Otherwise, don't go for checking for AC, because you can't find it, because it is already transitive. Similarly, 1 comma 3, there is no ordered pair starting with a 3. Therefore, you can't establish, you can't say that it is not transitive. If you are saying that it is not transitive, then you have to show that A, B, B, C belongs to R and AC does not belong, which you can't establish because it is transitive. So this is how to identify whether the given relation is reflexive reflexive, symmetric, or transitive. That is in the case in terms of sets, in the form of a sets notation, like taking one example of a set, then constructing the relations. There are other relations like parallel to. The relation parallel to defined on the set of all lines in a plane. You have to check, is it reflective? Every line is parallel to itself, so it is reflexive. Is it symmetric? If one line is parallel to another line, that another line should also be parallel to the first line, so it is symmetric. If L1 is parallel to L2 and L2 is parallel to L3, this L3, then automatically L1 should also be parallel to L3. So it is transitive also. The parallel to relation is reflexive, symmetric, and transitive. Now perpendicular relation is defined on the set of all lines in a plane. So every line is perpendicular to itself, which is not possible. So you can't say that it is reflexive. It is not reflexive. Every line can't be perpendicular to itself. If L1 is perpendicular to L2, then L2 is also perpendicular to L1. Therefore, it is symmetric. But it is not transitive because lies in a plane. If L1 is perpendicular to L2 and L1, L2 and L3 is perpendicular to L1, anyone. Okay, L1 is perpendicular to L2, L2 is perpendicular to L3. Okay, so in the same place, then L1 and L3 becomes parallel. If L1 3 also perpendicular means it becomes in some other plane, but it is all lines should lie in the same plane. Therefore, this is not transitive. Divides relation defined on every number divides itself. A divides A. Therefore, it is reflexive. If A divides B, B need not divide A. Okay, see 2 divides 4, but 4 does not divide 2. So it is not symmetric. It is reflexive, but it is not symmetric. 4 does not divide 2 means 4 can't be written as a multiple of 2. Okay, integral multiple of 2. That's why it is not symmetric. Then transitivity, if A divides B and B divides C, automatically A should divide C. Therefore, it becomes transitive. So divides relation is reflexive. It is not symmetric. It is transitive. So this is in terms of the general relations which exist between any two entities of mathematics. Parallel to between two lines, perpendicular to between two lines. This has to be specified because in a plane, if it is not specified, then perpendicular to relation also becomes transitive. So relation divides defined on the natural numbers, that is reflexive, not symmetric, and transitive. Then if you have the relation which is reflexive, symmetric, and transitive, all the three, okay, then we call that relation as a equivalence relation. A relation which is reflexive, symmetric, and transitive is called as an equivalence relation. This parallel to example is an equivalence relation, and similarly here the first relation R1 is an equivalence relation, and moreover this R1 is identity relation because this contains identity relation definition is set of all ordered pairs of the form A comma B such that A equal to B. If the relation contains only the ordered pairs of the form A or A equal to B, then we call such a relation as identity relation. So every reflexive relation need not be identity relation, but identity relation is always a reflexive relation. See, for example, this is identity, R1 is identity relation, R2 is not an identity relation because other than 1 1 2 2 3 3 it contains 1 comma 3 where 1 is not equal to 3. A equal to B, first element should be equal to second element. Such are relations only considered as identity relation. So this is all about types of relations. So in the next video I'll be coming up with the equivalence classes and some problems related to the relations. Thanks for watching.